Hello, my name's Andrew Earnest, and this is my colleague Nick Meyer. We are two of the co-authors of this paper entitled Strictly Regular Quaternary Quadratic Forms and Lattices that will appear in the Journal of Number Theory. We're at the Department of Mathematics at Southern Illinois University this morning. Our third co-author on the paper is Ji-Young Kim from Seoul National University, who was here in Carbondale visiting with us during the time that the research that we're going to talk about was conducted. Her work was supported in part by a grant from the National Research Foundation of Korea. As the title of the paper suggests, our results can be formulated either in the classical language of quadratic forms, integral quadratic forms, or in the modern geometric language of quadratic lattices, which is what I've chosen to adopt here. Specifically, by a lattice, I will always refer to a primitive integral z-lattice on a positive definite quadratic space over Q, the dimension of which will be denoted by n. The notion of regularity that we're talking about in this paper goes back to a paper of L.E. Dixon in 1927, where he introduced the term regular to refer to certain ternary quadratic forms. It formulated in the lattice terminology. A lattice L is regular if the local global principle for representation of integers holds for L. In particular, if every integer that's everywhere locally represented by L is actually globally represented by L. So, in particular, every lattice of class number 1 has this property of regularity, but it turns out that the converse is not true. So in the case when n is equal to 2, it follows from classical results on binary quadratic forms that in fact regularity is equivalent in that case to the condition of class number 1. So the first case where something new and interesting occurs is when n is equal to 3. The regular ternary forms and lattices have been studied extensively by a number of authors, and I've indicated here basically the starting and ending points of those investigations. The fundamental result here is that there exist only finitely many isometry classes of those regular ternary lattices, and that was proven essentially in Watson's thesis in 1953. And then over 40 years later, the enumeration of all of these isometry classes was completed. There are 913 of them, all of which are known. The case n equal to 4 is the subject of our current paper. Here something, a new phenomenon occurs, namely there exist now infinite families of non-isometric regular quaternary lattices. This has been known since 1995. So in order to get some finiteness result for quaternary lattices that's analogous to the one for ternary lattices, it's necessary to impose some sort of a stronger regularity condition. One way of getting such a condition is to come back to this definition of regularity, and instead of looking at arbitrary representations as we did here, we can restrict only to the case of primitive representations, both locally and globally. That gives a stronger property that Watson referred to as strict regularity. The main theorem of our paper then is that there exist only finitely many isometry classes of these strictly regular quaternary lattices. As with any finiteness result of this type, it's a natural question to ask whether it's possible to actually enumerate all of these finitely many isometry classes. We've undertaken that project in the special case of diagonal lattices, and we found that in fact there are exactly 96 such isometry classes, and the largest class number occurring among those lattices is 7. The results of those investigations are going to appear in a future paper. With regard to possibilities for future research, this theorem opens up the door to several possible directions of generalization. I've mentioned 2 of them here. One would be to find an analogous result for the representation of lattices by lattices, rather than just the restricted case of the representation of integers. And another one would be to investigate lattices over more general rings, particularly the rings of integers of totally real algebraic number fields would be a natural question to look at. I think it'll be interesting to see whether there are any generalizations of this type that will come forward in the future. I hope that this introduction to our paper has been helpful to you, and I thank you for watching.